Now let us explore the dead time. Now, before giving you an idea of dead time, let us draw a chromatogram. This time I will be drawing a little big one so that we can define certain terms. Now again, on the y-axis, we have the same thing, that is the detector response. And on the x-axis, we have time. Now, what can be done is that you can also plot x-axis with regard to the mobile phase. Mobile phase, which you are adding on a continuous basis. So it can also be plotted with regard to the mobile phase. But let us, for simplicity, let us take in terms of time. Now for a two component, or let us suppose for a simplicity, let us suppose a one component system. Now if you draw the detector response of the elution of a single component, you will see an initial first peak like this. Then you will see a peak like this. Now on the x-axis it's time. Let us draw a perpendicular. Let us draw a perpendicular here. Now this time is called as Tm. Okay, and this time is called as Tr, and this time in between it is called as Tr dash, and sometimes you can find it as written as Ts. Now we have three different times, that is the Tm, that is the Tr, and the Tr dash or Ts. Now this Tm gives you the time when you pass only the solute. Simply the neat solute is passed, that gives you the peak, that gives you the detector response in terms of peak. That first peak actually tells you that this your solute is not having any sort of interaction with the stationary phase, and that is why it is called as dead time, or sometime it is also called as void time, that is unretained solute. And it is actually, you can say, it's the standard, like in, for example, in NMR we call it TMS. So in chromatography, the TMS can be equated with the Tm. Now you actually record all your responses with regard to Tm, because Tm is the time taken by the mobile phase, which does not contain any of your analyte. That is for your neat mobile phase, neat solute, which you have initially passed through the column. Now there are certain markers, there are certain compounds which does not gets retained, which does not interact with the stationary phase, and the examples are the methane in gas chromatography, similarly uracil in high performance liquid chromatography. These are the substances which does not react, or which has zero interaction with the stationary fluids. So Tm actually provides you a baseline for relative retention calculations. So it's a sort of reference point, it's sort of starting point. That is, on the basis of this starting point, you measure the retention time of the other solutes or other components present in your separating mixture. So advantage is that it acts as a reference point, and the limitation is that, ideally speaking, it requires non-interacting compounds. But practically speaking, there is certain interaction, but that can be ignored because we are starting from this. So the relationship can be written as Tr is equal to Tm plus Tr dash, or it may be written as Ts. Now, the point which is to be elaborated at this juncture is this, that this Tm is because of the non-interaction of your mobile phase, and this Tr retention time is because of the interaction of your components with both stationary phase and mobile phase. Mind that. It's not alone with the stationary phase, because you have added TM also, because your TR contains TM part. Your TR contains GM part, so it has already accounted the interaction with the mobile phase. So TS actually is simply the plane interaction of your components with the stationary phase alone. Are you getting my point, my students? So this is actually very interesting. That is, on the basis of time, you have quantified it in three terms. That is the TM, that is the TR, and of course the TR dash or TS. So you have accounted for the interaction of the mobile phase. You have also accounted for the interaction of stationary phase. And all these three quantities you can measure directly from the chromatogram. So what is the difference between KD and TM and TR and TS is that the KD gives you a very good idea about the column performance. It gives you about the interaction, but it cannot be measured in. But on the other hand, you can measure all the TRs. That is, you can measure TR, TM, and TR dash directly from the chromatogram. So now it's time to actually, establish a relation between these two, because one is measurable while the other is not measurable, but it is, giving you very important information. And similar to KD, TR is also very specific, very characteristic for any chromatographic separation. We will going to see this in our coming slides. So TR is actually the time taken by the solute from the injection point. From the injection point, now suppose this is your packed column. Packing starts from this point. So TR is actually the time taken from this to this up to the elution. So we have three things. Number one is the TR, that tells you about the retention time taken by the solute in the mobile phase to reach up to the column, to reach up to the detector, sorry. And then the second time is the void time, and third one is the time taken by the interaction for the stationary phase, interaction of the solute particles with the stationary phase. So we have three things. We have TR, we have TM, and we have TR dash. So it gives you interaction of the stationary phase, stationary and mobile. It's give interaction only with the mobile, and it gives you only stationary. And fortunately, you can measure all the three. You can measure all these three quantities from the chromatogram. So let us, so this is TM, is called the hold up time or the dead time or the void time. And this is the additional retention time due to interaction with the stationary phase. So you can see TR, or sometimes you can see TS also. So don't worry, this both are the same, okay? So a classical example is the benzene. Benzene actually has a TR of 5.2 minutes and toluene has a TR of 7.4 minutes. Why the difference is there? The difference is because of the difference in polarity. Simple. It's non-polar, so it is eluting very fast. It is a little bit polar, toluene. So it is eluting at a low rate, or it is taking more time as compared to benzene. This data is from the GC, that is gas chromatography. So what we infer is that retention time of any compound is specific under given conditions. Now, what are the given conditions? Given conditions are, of course, it is the temperature. Again, temperature can affect, and the pressure. Now, what we can see, we can say that KD and these are thermodynamic in nature. They are thermodynamic parameters. They are not simple parameters, they are thermodynamic. So what are the factors which affect this TR? Number one is the column length. Now again I am correcting it. Simply column length or packed column length or packed column length. Packed column length. This is more specific. And then of course flow rate, that is V. Okay. And specifically again average flow rate, because we always talk about the average quantities. Similarly parameter and the stationary phase. So these are the factors which affect the retention time, TR. Okay. So now it's time to relate the two. That is the retention time and the distribution constant or distribution coefficient. So what we have seen that higher K value means that longer retention. Now, if you remember from our previous slide, we have this relation TR is equal to 2m plus TS or TR dash. Now let us derive in terms of the KD value. So what we were having is this. Let us now relate the two quantities. One is the measurable quantities and the other is the non-measurable quantities. We have seen in our previous slides that KD is giving you information, but it cannot be measured directly. And what you can measure directly is the TR, is the TM, and of course it is the TR dash. So on the basis of this, an approximate relation can be drawn like TR, that is the retention time, can be defined as Tm into 1 plus K upon Vs upon Vm. Vs is the volume of solute in the stationary phase. Vm is the volume in the mobile phase. Now TR is the retention time and Tm is the dead time. So we have already seen that if any substance has higher K value, higher Kd value, then it means that it is having a stronger interaction, and the stronger retention actually gives you larger or longer retention time. So this actually retention reflects the partition equilibrium. That is where the partitioning is going to happen more. We can also derive another relation. For example, we have described that the average velocity, for example, the average velocity we have defined in our previous slides of solute in the mobile phase. In the mobile phase, we have defined by nu, while the average velocity of mobile phase only was given by u. It is nu and it is u. Now let us draw a relation. Now you can define like this, that nu may be defined as, or let me draw it more clearly. Nu may be defined as u into the fraction of solute in the mobile phase. This we can have the relationship, that is the average velocity of solute in the mobile phase can be equated with the velocity of the pure mobile phase into the number of, or into the fraction of solute in the mobile phase. Okay, it's a clear cut relation. So this can also be written as u into, now the fraction, that is this fraction can be defined as Cs. Then the mobile phase, you can say that it is actually the Cm into Vm, that is the solute or number of moles in the mobile phase upon number of moles in the mobile phase and number of moles in the stationary phase. We can write like this. That is what we have done. We have done in terms of number of moles of solute present in the mobile phase in terms of CMVM, because if you remember, we have described it as Cm upon Vs, Cs upon Vs. We have described like this. So it is the same. So what happens is, now if you take this and solve this, you can get divided by Cm Vm upon Cm Vm divided by Cm Vm upon Cm Vm plus Cs Vm upon Cm Vm. Okay, this is the relationship. What we have done, we have divided with the similar quantities. So this gets cancelled with this, giving you 1. This gets cancelled with this because numerator and denominator are the same. Here also it gives you 1, and here if you solve it, you will get like this. If you solve it further, you will get like this: u into 1 upon 1 plus Cs Vs upon, it's actually upon Cm Vn. Here also it is Cs. It is also Cs Vs. So what we get, u plus u into 1 upon 1 plus, it is nothing but it is Cs, it is actually Kd upon Vs into Vm. So you can derive in terms of your dead time, you can also derive in terms of your mobile phase velocity only. So you can derive in both ways, whatever actually suits you, what type of data is given to you. Okay, so you can have two relations, that is, you can derive it in terms of V and you can derive in terms of U. And the beauty is that these can be measured. So retention factor. Now retention factor is very important. It gives you an idea, a quantified idea, that how much the solutes is going to retain in the both phases, that is in the mobile phase and in the stationary phase. And this is actually denoted by K dash. And K dash can simply be defined as Tr minus Tm upon Tm. That is the retention time minus the dead time upon dead time. In fact, you can also quantify it like, you can also quantify K dash is equal to the Ka or Vs upon V. You can also define like this. Okay, if you are dealing with solute A, or you can also write like this, that Kd into Vs upon Vn. The solute in the stationary phase divided by solute in the mobile phase. So what does actually K tells you? K tells you that if the value of K is 0, then your solute remains unretained. That is, there is no interaction. Your solute does not interact with the stationary phase. And as the value of K increases, it implies that it is going to retain in the column for longer times. And longer retention means stronger interaction. So for an optimum analytical separation, the K value must lie between 1 to 5. 1 to 5. At the most up to 10. But if it is greater than 10, then we can get a broad peak like this. And broad peak means that your column is actually inefficient, not working ideally. So the K value actually decides the utility or the importance of your separation. Now, what are the significance? We have seen that in terms of value, that if the K value is 1 to 5, it is good. So it is actually a dimensionless parameter, and it is independent of the flow rate of the mobile phase. And it is very ideal for comparison of more than one solute or more than one, you can say that, components. And it gives you a balance between the resolution and time efficiency. So now comes the selectivity factor. The selectivity factor is very important because it gives you an idea about the relative interaction of more than one solute. For example, for two solutes, you can define this selectivity factor as K2 upon K1. That is component 2 and component 1. And this K dash is actually the, which we have discussed, is the retention factor. So now you have another parameter which gives you an idea about the interaction of your solutes with the stationary phase and mobile phase. So for example, that K2 value dash upon K1 value is giving you that this K2 or component 2 actually, component 2 is having more retention time, having more. It is actually giving you an idea that is having more retention time. And if alpha, that this alpha is equal to 1, then you have no separation. That is, your peaks are actually, overlapping on each other. This is actually the story with it. So always remember that 2 means that its peak is actually, if you have a 2 peak system like this, then you can have, this is component 1 and this is component 2. So the upper part is actually telling you that this is going to retain for a longer time and this is actually eluting at a faster time. So always for practical separation, the limit is alpha should lie between 1.05 to 2. And again, it's a dimensionless quantity. It does not have any unit. So for example, we have given an example of leucine and phenylalanine. In reverse phase HPLC, its value lies, the value of alpha lies 1.8. It means it's a good separation. And moreover, if its value is too high, then the peaks are, far more to apart. Again, this is not a good separation because it is telling the story that it is taking too much time. So always you have that, that range, that is 1.05 to 2. That is the ideal range. If it is 1, then you have an overlapping peak. Okay. And if it is greater than 1, then it's fine. But it must be greater than 2. So that is actually gives you about the relative separation. So for an ideal separation, you have 2 well-defined peaks whose bandwidth is to be kept as small as possible. So this is an ideal chromatogram. And here you have the detector response. So this is how your alpha actually dictates the whole process of separation. So what are the factors which affect the selectivity? Number 1 is the mobile phase composition. This is very important. Again, solvent polarity dictates all these factors. That is how much polar solvent you are taking. And you are taking solvent on the basis of the nature of the compound which is to be separated. Similarly, the stationary phase chemistry. That is which type of stationary phase you have chosen. That is, you have chosen a polar stationary phase or slightly polar or exactly non-polar. And again, temperature comes into play, pressure comes into play. We are going to see the effect of temperature in a very detail in our next slides when we are going to discuss the gas chromatography. So what are the basically advantages of this? The first advantage is it is one of the most powerful factor in improving the separation. So on the basis of the value, you actually decides that whether you have achieved a good separation or not. And the limitation is that it is difficult to optimize predictively. You cannot initially you cannot say like this that it is going to have a good separation or not. So you have to run chronogram each time. Otherwise, you cannot say anything about it. So the interpretation of selectivity, that how selectivity is significant. Selectivity is actually a measure that how different solutes in a column are interacting with each other. Okay. So for a good separation, they should have a good separation between among them. Okay. So their values must lie between 1.05 to 2. And similarly, we can modulate the selectivity factor by changing the stationary phase. Okay. By changing the, actually changing stationary phase means changing the polarity of stationary phase. Similarly, we can change the polarity of the solvent system also. That is whether we are using some non-polar or polar. Now again, the thumb rule comes into play. For example, if our stationary phase is non-polar and we are using a polar solvent, then it will, it will elute very slow. It will take too much time. But again, for a non-polar combination, it is a good combination. It will elute in an optimal way. Similarly, we can also change the selectivity factor by adjusting the pH in case of ion exchange chromatography, where the separation occurs on the basis of charge. So charge comes and the pH comes into play, because then acid-base character also comes into play. So by adjusting pH in ion exchange chromatography. So what is the relation? Let us briefly see that what is the relation between retention time and retention factor. The retention factor is K dash. We have described it with K dash. It is Tr minus Tm upon Tm. So if we have taken a very small example, very simple example. If Tr, for example, if you draw a chronogram, then what is happening is that you have Tm coming at 2 minutes, then you have the Tr which is coming at 12 minutes. Now this is coming at 2 minutes, 1 0, and this is coming at 12 minutes, for example. Okay, now you have 4, you have 6, you have 8, you have 10, and you have 12. So K dash can be calculated. You have to simply put the value 12 minus 2. 12 is the TR and 2 is the TM, the dead time, which is this peak, dead time, TM. And this is the TR. This is the TR, which is actually 12 minutes. And this is TM. This is 2 minutes. So 12 minus 2 is equal to 10 upon 2, which is 5. So solute, this implies that solute spends 5% more time in a stationary phase than the mobile phase. This is how you relate your numerics with the interaction. So it is interacting 5 times more in the stationary phase than the mobile phase. Now resolution, another important feature on which this is actually the basic feature, resolution. Resolution with regard to peaks. So greater the resolution, better will be the separation between the peaks. So we have to have as much resolution between the peaks as possible. Again, it is for a two-component system. It is given as RS may be defined as TR2 minus TR1 upon W1 plus W2. Now, what are W1 and W2? Let us see. Now we have a chronogram. We have a TM. Then we have a this. Okay. Now these are two well-defined, well-resolved peaks. Now let us draw a perpendicular. Let us draw a perpendicular here. Now, for example, this is peak number 1 and this is peak number 2. Then this is called as W1 up to this point. And if you draw a perpendicular, now from where you have to draw a perpendicular? That is important. So you have to take the fronting part here and you have to take the tailing part here. Similarly, for dropping the perpendicular, you have to take the fronting and you have to take the tailing part. So you have to take that the medium, where maximum elution is taking place. So you have to take the maximum part. This is W1 and this is W2. This is TM, half of this. This is TM and this is, you can say, TR1 up to this point, and this is TR2. So your resolution is defined as twice of TR2 minus TR1 upon W1 plus W2. So W1 and W2 are the baseline peak widths. For a good resolution, RS must be greater than 1.5. That is, this distance must be greater than 1.5. Okay, so for an effective chromatographic separation, RS value must always be greater than 1.5 for effective separation. Now let us see in terms of migration rate. Migration rate, we have already told you, is given by the velocity of migration, or migration rate is given by in terms of the solute movement, given by V is equal to L upon TR. That is the length of the packed column. TR is the detention time. So if you have a large value of V means that you have a small value of TR. That is, it is weakly retained. It is going to elute very fast. Similarly, if you have strongly retained, so you have a small V value. Now, a migration rate with regard to retention factor, we are going to see. So, what are the factors which affect the retention parameter? Of course, it's the column length and the packing in it. That is, the greater the column length, greater will be the separation or resolution. We have to adjust a flow rate. We have seen the previous slide. Temperature is again important. We will be going to discuss it. Mobile phase polarity and pH, and the nature of stationary phase, whether it is polar or non-polar, that is hydrophilic or hydrophobic or ionic. So these are the factors which directly affect the retention parameters, that column length and packing, that longer the length, greater will be the resolution. Flow rate must be optimized. Similarly, temperature, it has to be maintained. For isotherm, we will see that we have to have isothermal ovens, and the mobile phase polarity, it must match with the polarity of the stationary phase, because again we have a strong interaction for polar, and we have a weak interaction for polar non-polar. So let us briefly go through some of the practical examples. That is caffeine. It is actually here the water methanol, it is a mixture, and the stationary phase is C8 silica gel. We observe a caffeine peak and retention time of 6 minutes. It is at about 6 minutes. Okay, 6 minutes. Here time, and time is in minute. It is the detector response. So caffeine, it is eluting at after 6 minutes, and sugar elute earlier because it has a polar and it has a weak interaction. So the weak interaction will come first, the sugar will come first, then caffeine comes, then the caffeine comes because it is going to retain. And this is actually how the K dash and alpha gives you a good idea about the separation. Another example is the gas chromatographic separation of hydrocarbons, where we have used hexane versus octane. Octane has a very strong interaction, and a strong interaction means higher K value. That is large TR value. That is, it is going to retain. It is coming very slowly. So it will come at the end of the chromogram. Longer TR, large value. Similarly, selectivity, always it is should be greater than 1, so that we can have a visible peak separation. That is, the peak should not like this. It should be clearly resolved. Okay, it should not superimpose on each other. So it's not good. It's an ideal system. Okay, and this can be achieved if we have alpha, that is selectivity factor, greater than 1. Now another example is the protein ion exchange chromatography. Here the proteins have different charges, and because of different charges they have different retention times because they migrate at different rates. Now by altering the pH or the salt gradient, it can be tuned, because now you induce certain parameters, and because of that certain factors of positive and negative charge comes into play. That positive will attract the negative, and because of that the selectivity factor can be changed, or it can be fine tuned. Now let us summarize the various equations which we have derived. So initially, first of all, we have derived the distribution constant Kd. We have written it like this, Kd, so do not get confused. Where the small t comes, it is all the way same. That is small Kd or Kd. So we have defined in terms of Cs upon Cm, that is the molar concentration of analyte in the stationary phase upon the mobile phase. Similarly, it depends upon the affinity, and here it is the it is because of the migration equilibrium. So an example is the polar analyte in the silica gel. Similarly, we have defined TR. We have, if you remember, it is TR like this. So we have defined in terms of TM, that is the dead time, and the extra retention time, or it is because of the interaction with the stationary phase. Now it depends on the flow rate as well as the KD value. The KD value. Significance is time of detection. So we have seen example is the caffeine peak at 6 minutes while the sugars elute very fast. We have seen it. Again, it's the K dash, that is the, you can say, retention factor. It was defined in terms of TR upon minus TM upon TM. Again, it depends on TR and TM. Okay. So the significance, it tells you about the relative retention rates. For example, it's a 2-component system or 3-component system. It can be decided on the basis of its value, that is K dash value. Similarly, we have the selectivity factor, which actually relates the separation of the components. We have seen in terms of octane and hexane. And the last one is the resolution, which was given in terms of an equation, that is TR2 minus TR1 upon the width of the peaks, that is W1 and W2. So these are the actually factors on which it depends, and it gives you about the significance of the peak resolution. The significance is the peak resolution. We have a very good resolved peaks. And a common example is the amino acid separation on the basis of their positive and negative charges. So what are the practical advantages of elution chromatography? Elution chromatography gives you a very good resolution, and of course it is reproducible. You can do 5, 10 or 20 separations and you will get the same values each time. So this is actually the reproducibility. So it has very good reproducibility. Now it can separate complex mixtures. Okay. Similarly, again, it is quantitative and qualitative information. Qualitative, it gives you the nature, and quantitative, you can calculate under the area of the peak. Okay. So versatility is, it can be used in GC, HPLC, ion exchange, as well as size exclusion chromatography. So what are there are certain limitations also. Now the first or the foremost limitation is the time. Sometimes it becomes very time consuming, because sometimes they different components which are to be separated, it gets very strong bond with the stationary phase, and once they get strong interaction, they are going to retain for longer times, and this longer retention actually gives you a longer application, or longer time for separation. Peak tailing occurs due to secondary interaction, that is, the peak is not sharp. It actually, you can see that it goes on tailing. Similarly, sometimes fronting also, it takes very long time to reach. The ideally, your peak must be Gaussian like this. Ideal peak is this Gaussian peak. No fronting and no tailing. This is tailing and this is fronting. So an ideal peak must be Gaussian. Ideally, Gaussian peaks are there. Gaussian peaks are to be obtained. Sensitivity to temperature, that is, on increasing the temperature, you can change it. Okay. Sometimes it is beneficial, while sometimes it is not. Again, the high cost for advanced column. For example, if you are using sophisticated columns made of glass or made of steel, sometimes clogging occurs. And because of this, it limits its use. Okay. So what are the real life applications where we can use the elution chromatography? Of course, we are exclusively used in pharmaceuticals for the purification of drugs, for profiling, for checking the impurities. Similarly, forensics, we have already discussed that it is used to ascertain the poisoning, to ascertain the drug abuse, or sometimes to check the rash driving, where people drink alcohol and they go on rash driving. So that alcohol content can be checked by simple test. Similarly, in food safety, it is very important, because now it is mandatory to give you a clear-cut profile about the different ingredients present in it. Similarly, with regard to environment, it gives you a very good idea about the certain pollutants present even at trace and nano levels. So, drug control studies, paracetamol tablet, retention time actually confirms the drug identity. Similarly, resolution gives you an idea about the purity, that how much pure your sample is, and the selectivity confirms that it does not contain any excipients. So it is actually very good with regard to drug control. Similarly, advanced insights. What are the what are the things which are going under the background? So retention behavior is actually influenced by certain weak interactions. Number one is the pi-pi interaction, which generally happens in case of aromatic compounds. Similarly, hydrogen bonding, when uh, when 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 an atom gets in between two electronegative centers. Two electronegative atoms. Then hydrogen bonding comes into play. So similarly, we have ionic interactions because of the charged solute. Now, we have seen a lot of advantages of KD, but KD alone cannot explain all the things. This KD can be write this, okay, KD. So it's not something different, it's the same distribution constant. So what are the hidden retention concepts? So practically TR must range from 2 to 15 minutes. For example, in HPLC case, the shape of the peak must be Gaussian in nature, and there must be no tailing. That is, there must be no secondary binding with the stationary phase. So what is the optimization strategy? How we can have good results from the column, or how can we have effective column separation? Number one is we have to ensure the retention factor that it should range between 2 to 10. We have to adjust the selectivity factor according to column and according to solvent with regard to the polarity. Similarly, we have to monitor RS, that is, the peaks must be well resolved. It's not overlapping or it's not superimposing on each other. It must be separate. Okay, and the peak must be have as small width as possible. So it is very important to optimize the column, and these are the three important steps to optimize your column. So in the end, let us summarize what we have, what we have studied. Initially, we have to inject our sample. Then there's a dead time or void time, that is the time taken by the mobile phase alone to elute from the column. It is given by dead time. Then the retention time, that is the time taken by the solute along with mobile phase, that is called the TR. Similarly, capacity factor, the retention factor, you can say like retention factor and capacity factor are those same. Then we have the selectivity, and finally we have the resolution. On the basis of resolution, you can say whether you have done a good separation or not. If not, then you have to optimize your separation. And how we have optimized, we have seen that the optimization. So initially you carry out the injection of your compound which is to be separated, then you get the TM value, dead time, then you get TR. On the basis of TR, you calculate K dash, because KD is not measurable directly. So you run all the data in terms of TR, then you calculate K dash, then alpha, then the resolution. And then after certain optimization, if needed, you get the optimized separation. Okay, so this is how the elution chromatography works. Okay, so what are the future perspectives? Now, nowadays, we are more concerned with the environment. So we have some eco-friendly solvents. We do not have to use every time very toxic solvents. So most of the time we have to rely on the eco-friendly. And the most eco-friendly solvent is, of course, our delicious water. But the water is actually making problem because it is very polar. So we have to optimize in terms of green solvent. Similarly, we have to have small. We can separate. We can be able to separate very small samples. That is, we can have microfluidic columns, because these days traditionally we use very long columns, because sometimes this long column is needed to have a better efficiency. because nu is equal to L upon TR. So we cannot compromise with the length of the call. Okay, so nowadays, AI is out everywhere. AI means we have to use the artificial intelligence in a very intelligent manner, along with the machine learning, that is the ML. So we have to use AI and ML hand in hand to have a very good retention prediction. Before running in a lab, we can get an idea that which type of solvent is better for which type of stationary phase. So if we get an idea, then it will be definitely, it will save our time. It will save our resources. Then we can use the more high fidelity technique like liquid chromatography, mass spectrometry, or the gas chromatography, mass spectrometry. So we have to use all these in our future. So future for chromatography is very bright. So with this, thank you very much. Thank you all.